So, hello everyone. Again, we are about a quarter of the way through this course. It is Friday of the second week during the summer session. Remember there will be a quiz today, and it closes tomorrow at 11:59 p.m. Eastern time. Make sure you do quiz 2. Let's see, homework 2 due on Monday. And of course, we have exam 3, or well, the third week exam number 1 coming up on next Friday and Saturday. So make sure you're studying for that. You should find materials in Brightspace that'll help you study, including the equation sheet and some practice exams with solutions. As for homework 1 grading, we're trying to get that out hopefully by next month, before next Monday, so everyone has a chance to get feedback from their first assignment before they have to submit their second assignment. It's just a long, painstaking process, especially with problem 3, the design problem. If you feel like we've been overly harsh when grading, please submit a regrade request, making sure to email directly the person whose initials appear at the top, because that's the name of the initials of your grader. All right. Yeah, the students are talking about getting close to the threshold voltage for this class. So my goal for the threshold voltage is to have at least 30 students appear before I start lecture. And the 30th one just showed up. A+ for everyone. No, not quite that easy. I'll give you an S for satisfactory, just like a seminar. You'll take it. Extra credit? I don't know. I don't think there'll be extra credit in this class. We just don't have the grading capacity and the ability to really conduct it fairly with everyone so asynchronous. However, I do like to throw in these little tidbits before the start of lecture for people who want to know what's coming up on the quiz and homework. So something coming up on the quiz. Let's see, what can I reveal to you? Well, the question I wrote on the quiz has to do with solutions to ODEs. So you will see something about how you solve ODEs on the quiz. So anything more than that, I cannot reveal. All right, let's go ahead and get started. We have reached 31 students live today. So a quarter of the class is here. Are the quizzes in general going to be more qualitative? Yes, Arjun, I would say, yeah, qualitative. There are mathematical ideas. You can have some quantitative things, but like nothing that would require a calculator. The first exam will not be 3 questions, Keaton. The first exam is going to be 5 questions. Oops. Screen's pointing a little too far up. 5 questions. It's a 60%, 40% split, and also 60.40% split between lecture set 1 material and lecture set 2 material. As for which one is 60 and which one is 40, I'm going to leave that as a surprise. So definitely make sure you're mastering all the lecture set 1 and lecture set 2 material. If you get feedback on your homework about things you should study or that you should go to office hours, please do so. All right. Let's go ahead and, is there a homework regrade? Yes, homework regrade request. According to the syllabus, you follow the procedure. Make sure you CC the person whose initials appear at the top, or you directly email them. And then, yeah, I was telling people I may have been a little overly harsh. And you have 1 week until the solution is posted to submit a regrade request. And given that the solution isn't even out yet, you should be pretty good. All right, share screen. Let's get through some material, and then maybe at the end of lecture today, we can take more questions about, or at least after we finish lecture set 2, we'll take more questions about structure, administration, and what's coming up. So last time we finished discussion of the LC tank circuit and went over the RLC circuit. So here we have a series RLC circuit, or RLC, where we have the constitutive equations for all 3 of these devices, where we write the voltage drop across each one. Note that they all have current IL in common. Then you can basically get Vn of t is equal to LC times d squared dt squared of Vc of t plus RC times ddt of Vc of t plus Vc of t itself. Notice that in the so-called undamped case, not underdamped, but undamped, there's no resistance, R equals 0, and this middle term would disappear, and we're back to a series LC tank circuit. You can set up the characteristic equation, and you can get it into this form. 0 is equal to lambda squared plus 2 sigma p lambda plus omega naught squared, where lambda 1 and 2 are going to be, by the quadratic equation, negative r over 2l plus or minus square root of r over 2l quantity squared minus 1 over LC. Where we have the following definitions to make things a little bit easier. These, two or three ideas really make things a lot more tractable in terms of keeping track of things mentally. So in terms of circuit quantities, we have sigma p is equal to r over 2l, omega naught is 1 over square root of LC, and omega d, the damped resonance frequency, is square root of omega naught squared minus sigma p squared. Now, one thing I forgot to mention was units. Let's not get too tripped up with units here. So omega naught or sigma naught, one more time. That is omega sub 0, the natural frequency, and omega sub d, the damped resonance frequency, are both radial frequencies. So we expect them to have units of radians per second squared. And remember, radians is a very weird unit, as long as it's inside, a trigonometric function like sine or tangent or something like that, it basically acts like it doesn't exist. And, you can do weird things where it doesn't matter if you're keeping track of radians or not. The seconds, though, is important because it reminds us that all our solutions have to be multiplied by time in the argument. Sigma p is in units of r over 2l, which is Nepper's, abbreviated capital N lowercase p, and then per second. So overall sigma is in units of Nepper's per second, NP divided by S. And Nepper's is a similarly weird unit where it is most at home in the exponent of an exponential or as the argument of a hyperbolic function like hyperbolic tangent or hyperbolic sine. And Nepper's just weird, as long as, it's the only thing left, it doesn't really matter. You can act like it's not there. But Nepper's is kind of like, the argument of a base E logarithm, kind of like Bell's, which we are more familiar with as decibels, is kind of, the result of a base 10 logarithm, or another way to say it is it's in the exponent of a, base 10 exponential. So Bell's, Nepper's, radians, all sort of weird units where they're at home as the argument of other functions. In any case, we have to talk about the cases of the solution to determine what functional form we get. We have the overdamped case, sigma p squared greater than omega naught squared, which produces real and distinct roots. The critically damped case, where there's equality, and the underdamped case, where there's a less than sign. Real and distinct roots means we have, the sum of two exponential decays. Critically damped means we have an exponential decay and then an exponential decay with the same variable, with a t multiplier out front. And then underdamped means we have, an exponential decay times, a sum of a sinusoidal and cosinusoidal component. So that's what we talked about, and these are our conditions. And we did the parallel case in detail, but here's the nice summary with the series RLC case. And then, we left with a caution that as you add more resistors, the order is determined by the number of non-trivial reactive elements, so non-trivial amount of inductors and capacitors. Adding resistors makes things more difficult, but doesn't really change the solution strategy. What questions do we have? Everyone's an expert on differential equations, or at least the constant coefficient linear ones. Hope so. Math 262 trade as well. Ah, you took 262. All right. So that covers that. So now we're onto a switch circuit. So what we're going to do for a switch circuit is basically before the first temporal boundary, generally t equals 0, or t naught being 0, there's some sudden action that occurs, and then we use the state values, generally capacitor voltage and inductor current, as initial conditions immediately after the temporal boundary. So these things generally cannot change instantaneously. So inductor current at time t equals 0 must be that at time t equals 0 plus. Capacitor voltage at time equals 0 minus must be equal to that at time equals 0 plus. So we'll generate an ODE for the circuit topology after the temporal boundary. So we'll figure out, okay, what elements of the circuit are in play. And then we'll figure out the ODE. We'll find the complete solution, which is all those 10 steps we've been dealing with before. Solve for the state values immediately prior to the next temporal boundary, and repeat analysis from the beginning using the variable transformation. T prime is equal to t minus t sub k plus 1. So that way we can always work with t equals 0 minus and 0 plus, and t prime equals 0 minus and 0 plus. So that'll make our lives a little bit easier. So my assertion at in the last lecture was that you can solve any circuit with basically the turn on point being at t equals 0. So here's the circuit. We have this single pole double throw switch S1. We have this battery with V in. We have an inductor, resistor, and capacitor. And then we say the switch has been down for a very long time before switching up at time t0 is equal to 0. And it switches back down at time t1, staying there for the remainder of time. Furthermore, it's known that 4L is equal to CR squared. So because we'll go ahead and get started with our explanation. I'll leave this up for a little bit while reading from slide 49. So for t less than or equal to t naught, which is 0, the switch S1 has been down for a very long time. So it is expected that the circuit is at rest because the battery is in an open circuit. It's not really doing anything that would cause current to flow, at least. And then we are just left with this RLC circuit. So any energy that was stored in the magnetic field of the inductor or electric field of the capacitor should have been discharged as heat through the resistor. So that means we expect there to be 0 capacitor voltage and 0 inductor current at time t equals t0 minus. So again, no source in this loop. That's kind of what we expect. So this part of the circuit is at rest for t less than t naught. So between t naught and t, the initial conditions are that IL at t equals t naught plus and VC at t equals t naught plus must be 0 because the inductor current and capacitor voltage are not going to instantaneously change when we flip the switch. So the capacitor remains, discharged, unenergized, and the inductor remains degaussed, which means it's unenergized. There's no magnetic flux linkage inside of it. So the relevant circuit when the switch is up is just, this driven series RC circuit that goes kind of around the outside loop. So we can write that as a differential equation, and we can say that V in, which is that battery voltage, is equal to RC times dVc dt plus Vc of t. The solution proceeds just like the series RC circuit we studied previously. So we know that between time t sub 0 and t sub 1, Vc of t is equal to Vn times quantity 1 minus e to the negative t over Rc and quantity. You know, if you don't remember how we got that, you can go back to the start of lecture set 2, and you can see how we derived this sort of step response for the series RC circuit. But, you know, this is what we got. So at time, you know, now we have to figure out what happens at the end of the interval, which is, you know, step 5. So at the end of the interval, at time t equals t1 minus, the inductor current is still 0. It's, you know, been disconnected from the circuit. You know, the inductor sees an open circuit, so that means there must be 0 current running through it. And we need to find the capacitor voltage at time t equals t1 minus. And that's as simple as plugging in t is equal to t1 into our complete solution for the capacitor voltage. So notice this is just a constant. It's no longer a function of time because we've evaluated at a time instant. And then now we're going to evaluate, examine the next time interval by using the variable substitution t prime. A substitute variable is equal to t minus t1. Let's see what questions we have. ECE Math 266. Okay. Not seeing any questions, so I'll move on and we'll finish off this example. So at time greater than t1, the switch flips back down. So we have a undriven RLC circuit, so it's unforced, but you know there is a voltage in the capacitor at play to give this, even though there's no inductor current. IL at time t equals 0 plus must remain 0. Vc at time equals t1 plus must be that value that we just solved for. These quantities don't instantaneously change. The relevant circuit is an unforced series RLC circuit. So we'll, you know, do our work and figure out we have this differential equation. So we find the complete solution. So the roots are going to be lambda sub 1 comma 2 is equal to minus r over 2l. That's a typo, that's a carryover. Minus r over 2l plus or minus square root of r over 2l quantity squared minus 1 over LC. But we'll notice that, say we plugged in L is equal to 1/4 CR squared. You know, L is equal to 1/4 CR squared. So this becomes 1 over 4 C squared R squared. Plug something similar in for this side, and we'll see that the discriminant is 0. That means we're in the critically damped case. So conveniently, this problem was set up so that we have a critically damped RLC circuit. Exactly. So the homogeneous solution, V sub CH of T prime is equal to A1 e to the negative sigma P T prime plus A2 times T prime e to the negative sigma P T prime, with sigma P being R over 2L. Our complete solution VC of T prime is A1 e to the negative sigma P T prime plus A2 T prime e to the negative sigma P T prime. You're asking, why is there no particular solution? Well, that's because, again, there is no forcing function for this circuit. It's literally just, 0 is equal to our ODE, no forcing function. So we solve for A1 and A2. So we plug in at time T prime is equal to 0 plus. And then we have to take a derivative to get IL at time T prime equals 0 plus. So that's C times the derivative. Work that all out. at t prime equals 0 plus. And you get A1 is equal to VC of T1 is 0 plus, and A2 is just equal to sigma P times A1. So when you go ahead and write the capacitor voltage, you get this for VC of T prime. Where we have VC of T prime equals 0 plus as a constant. This is just a constant sitting out front of the bracket 1 plus R over 2L T prime. And of course, e to the minus R over 2L T prime. So I'll make that clear. So one last step is we have a bunch of different cases. We'll rewrite the complete solution for all time to the capacitor voltage, using our variable substitution, sending it back to time, and then writing VC of T1 plus as, this thing right here. So we'll get, VC of T is equal to 0 for time less than or equal to 0, that it's Vn times 1 minus e to the negative T over RC between 0 and T1, and then above T1, it's Vn times 1 minus e to the negative T1 over RC, which is just a constant, times the quantity 1 plus R over 2L times T minus T1 times e to the negative R over 2L times quantity T minus T1, close quantity. So that is our switch circuit. Maybe you want to figure out what this is like with some numbers, because that constant is kind of gross to deal with, or at least it takes up a lot of ink. So with a numeric example, we'll use a 1 kilo ohm resistor, a 50 microfarad capacitor, a 12.5 Henry inductor, big inductor, and a 10 volt battery. So down for a long time, switches up at t equals 0 and back down at t equals 2 milliseconds and stays there for the remainder of time. So tau for the circuit, the RC time constant for the series RC circuit is 0.05 seconds. Sigma p is 40 nepers per second. And then VC of time T1 plus is equal to 0.392106 volts. So it flips up, behaves like this, where it's going to be an exponential approach towards 10 volts, but it doesn't even get very far. It only gets up to 0.392 volts before it immediately starts, being a critically damped decay back towards 0. Maybe it'd be a little bit more interesting if we switch time T1 to be something a little bit bigger, maybe more like 20 milliseconds. You would get a more interesting result when you graphed it. But that does it for our switch circuit. Remember, nepers is a weird unit. It's at home inside, argument of a hyperbolic function or in an exponent. And then out here, arguably this nepers doesn't even exist anymore. When you multiply by time, it should just vanish to a unitless thing so that you can add it to the unitless one. Explain why there's, okay, AJ. Sorry, I called you Arjun earlier. Okay, so because if we look what happens after we've charged up the capacitor through the resistance, when we switch back down, we notice that this is just a series RLC circuit, but there's no other, voltage source in this loop to act as a forcing function. So this is an unforced circuit. So that means the homogeneous solution is also the complete solution. How do you get A1 and A2? Okay, so we know that at time t prime equals 0, we have a certain value for VC of t prime. So at time t prime equals 0, this is, some, value. In our numerical example is 0.392 volts. So we say 0.392 volts is equal to A1 times e to the 0, which is just A1. And then we have plus A2 times t prime equals 0 times e to the negative sigma p times 0, which is just 0. So that allows us to find A1 quickly. We're also given the capacitor or the inductor initial condition that it has 0 current. But we have to use the constitutive equation. IL is equal to C times dVc dt. Okay, because IC, the current through the capacitor, is also shared with the inductor. So IC is equal to dVc dt. So we can say that 0 is equal to, by taking the derivative of this right here, we get minus A1C times sigma p, e to the negative sigma p, plug in at time t prime equals 0. Take the derivative of this by the product rule, we'll get, a C times A2 times 1 times e to the negative sigma p, evaluate at t prime equals 0. And then we'll get a C A2 t prime equals to 0 times negative sigma p, all times e to the negative sigma p t prime at t prime equals 0. So I combined a bunch of steps where I took the derivative and evaluated into a single idea here. Does that make sense, AJ and Riyadh? Good. Glad. Do we have any other questions? Do we feel comfortable dealing with switches on our homework now? I hope so, because homework 3 is going to have switches on it, and the exam has switches on it.
I have a quick question about like step 9. Why are we still using like t prime equals 0? Because isn't that once the switch is switched back to make the RLC like closed loop?
Yes.
So why isn't that T1 instead of 0?
So there's two ways of thinking about it. We can think of it in terms of t variables, where this happens at time t equals t1. The other way to think of it is if you use our variable transformation. Remember, if you plug in t equals t1, that's equivalent to saying at time t prime equals 0.
Oh, okay. That makes sense.
Yeah, we specifically set up t prime such that we would be working with t prime equals 0. That's, I guess, the rationale.
Okay, thank you.
You're welcome. Any more questions? Yeah, that's the major event. Okay. All right. I'll go ahead and say we are done with lecture set 2 then. Yay. Do we have any questions about direction of the course, homework, exams, office hours, lectures, material? Basically, up to today is where exam 1 material comes from. That's how the circuit performs. The best answer I can tell you, Luke, is try plotting out the functions for a given LC and a variable value of R. I'll see if I can find like a Desmos or a GeoGebra or something where it lets you play around with the slider. The Wikipedia page is also pretty good. It shows you like how the time domain response changes, nice and continuously as you vary R and thus vary sigma p. You can work with just t and t1, but like you have to be very careful that when you use the time variable, you're always doing t minus t1 everywhere. So on. So be very careful with that. Yeah, getting used to variable transformations like this is, pretty typical in both classical mechanics and in circuits and electromagnetism. So like it helps to get comfortable with the idea of a time variable transformation, because after all, time equals 0 is a arbitrary concept. A human has to choose it. Time itself doesn't have a true 0 point. Well, you deal with differences in time. Any more questions? Hearing no questions, we'll move on to lecture set 3. So lecture set 3, this is also started on the 24th of June. So here is convolution. This covers chapters 13 through 17 in your book. So first of all, we'll discuss discrete convolution. Then we'll get into an algebraic approach to convolution, where convolution is some mathematical operation we're going to define, with simple causal functions being defined, function transformations, as a preparation for our convolution definition, and then a discussion of convolution properties. Then we'll talk about a graphical approach to the convolution. And then we'll switch topics a little bit and talk about impulse response and how it relates to convolution with some background examples. And then after we do that, we'll do a numerical approach to the impulse response, where we're going to use like numerical ODE solvers to find the impulse response. And also talk about how you can represent signals with impulses, whatever that means. So why bother to go through all this work to learn another technique to solve the circuits? We got one that works with the ordinary differential equation method. So why learn a second method to do the exact same thing? And the answer is that it is a pain to recalculate the particular solution to a circuit initial value problem, or IVP, for all inputs of interest. Right now, every time you change the input, so say you want to go from a step function to an exponential decay to a sinusoid to, maybe like a sinusoid times the multiplier t, all of that happens, and you have to recalculate your particular solution to the circuit, which changes your complete solution, which changes the undetermined coefficients you have to find. So it's a real chore. Furthermore, convolution is very useful. I would call it the fundamental operation of electrical engineering. I like to joke that, the fundamental operation of accounting is addition and subtraction. Most of them, maybe, finance has exponentiation. Business in general might be, multiplication, division. We get convolution as the fundamental operation for our major, at least for the electrical engineers present, and in many respects for the computer engineers too. So it's useful in circuit analysis. It works very nicely with the Laplace transform that we'll cover in lecture set 4. Signal processing, this is how you do sound and image filtering. Machine learning, suddenly that's the sound you hear of, 100 or so or 70 or so computer engineers suddenly paying attention to what I have to say, because I use the buzzword of machine learning. So it shows you how much your data matches a template, and are they the same thing? We'll let the computer decide. And then as the ECE 302 bit of forgotten knowledge, the probability density function of the sum of two independent random variables is the convolution of their PDFs. So before we look at continuous time convolution, it's a nice warm-up for ECE 301 to look at discrete time convolution. This is kind of an isolated topic within the curriculum. It's just kind of there as a preview and also as a conceptual warm-up for continuous time convolution. Besides, many real-world processes are accurately described and simulated on computers as many, many discrete events. So using the ECE 438 definition, discrete means there are separate or distinct events separated by some finite smallest interval. usually it's equally spaced, something happens, every, 0.1 milliseconds or something like that. But you can also have like something that like, gets smaller and smaller, but approaches some smallest interval that's non-zero. That's what it means to be discrete. So we're going to define a discrete time function called the Kronecker delta function. It's the unit impulse function of discrete time, and it's the identity function for convolution. By that we mean if we convolve anything with the Kronecker delta function, we're going to get that thing that we originally convolved. So we're going to use, lowercase delta, drawn like this. And then we have square brackets and the time variable n to, represent the fact that we're in discrete time. And then for any n integer not equal to 0, the function takes on a value of 0. And then at time equals 0, it has a value of 1. So this is a pretty straightforward explanation to understand. 0 for any non-zero time instance, at time instant 1, or time instant equal to 0, it's equal to 1. So this is a useful function to have. We also need a unit step function to act as the indicator of when a signal is non-zero. So now we're getting into the discrete time unit step. We've been working, or at least alluding to the continuous time unit step before. So this is u at, as a function of discrete time n. It's going to be 0 for all n less than 0, and then 1 for all time greater than or equal to 0. So you can see it's off, 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 and then on for the rest of time. So anytime we multiply a signal by the unit step, so say we were multiplying, something that, behaves like a discrete sinusoid by the unit step, you get a truncated copy that only exists past the turn-on point. So multiplying a sine function by the unit step would result in 0, 0, 0, 0, and then something that starts behaving like sine after time n greater than or equal to 0. Why is the unit step useful? Because when you convolve with the unit step, it gives a running sum of the other function. So it's like it's like the running sum function. Okay, a small value and then a bigger value, and then so on and so forth. So with that out of the way, let's get into the definition of discrete time convolution. So we say f of n convolved with g of n. Convolve is the verb that means to take a convolution. So f of n convolved with g of n is the same thing as f convolved with g of n. That is equal to the sum from m equals minus infinity to infinity of f of m times g of n minus m. So what we do, first of all, I got to note that this symbol right here is the convolution symbol. It is a type of asterisk, but it's not the asterisk that normally appears on your keyboard. You have to be careful because when you type the asterisk key, sometimes you get something else. So you must use a 6-pointed star to represent convolution. So whether that's the one with the vertical bar, like this one, or one with a horizontal bar, like I normally handwrite it, that is the convolution symbol. Do not use an 8-pointed star, do not use a 5-pointed star, do not use anything else. Those represent other things. And do not, mix and match, the star for convolution with the star for multiplication. That is a recipe for disaster if you start doing that, and makes it very hard to grade your work. But the thing is, it takes two functions of time variable n and spits out a new function of time variable n. Notice here, the m is just a summation index that we used in the definition. So when we take our result, since we're summing over it, m must disappear from the result. We cannot have m appear in our final convolution. So what we're doing is taking the function g of n, we're reflecting it on the m track, which is the track with the m variable. It's reflected horizontally, and then it is shifted along by a value of n after the reflection. So that says how far along it is after it's been reflected. We multiply by f of m, which is the same thing as f of n, just with a new variable inside of it, and then multiply the f of m by the reversed and shifted g of m at each time instant. And then finally, the result after multiplication is summed along all of the m line to produce a single time instant of your convolution result, f convolved with g of n. And then you move on to the next time instant, where you shift g one time instant further along, you multiply, and then you sum over all of time to get another time instant of your convolution. So there's a lot of math that underlies this operation. Luckily, we typically act with signals that only last for a finite amount of time. So the result is that the length of a convolution is the length of f of n plus the length of g of n minus 1. So here we have a signal of length 5. It goes from time n equals 0 to n equals 4. And g of n goes from time n equals 0 to n equals 3. It'll last 5 plus 4 minus 1 is equal to 8 length when convolved. So let's work out exactly what happens. So here is, the original functions. So put in as functions of n. So now we need to deal with what's going on here. Your book explains this using trains. I like to explain this, just the functions, but if you want a more visual picture of what convolution does, I suggest looking at the relevant textbook portions. So I am going to put this up here and read how we got here from slide number 6. So again, we are going to put function f of n onto the m variable track. So here is f of m. It's 0, and then in blue it goes 2, 1, 1, 3, 4, and then 0, 0, 0, 0, 0, for on and on and on. And then for g of n, we're going to first put it as g of m. So we switch to the m variable track. We reflect it. So that means we have it go backwards. So instead of going forward as 5, 1, 2, 2, 0, 0, 0, it goes backwards 5, 1, 2, 2, 0, 0, 0, 0. And then we add another shift of minus 1 here. So now, this function is backwards 1 from where it started. It's shifted left 1 from where it started after we did the reflection. So what we'll notice is that for any n less than or equal to negative 1, there is no overlap between these functions. I graphed the function collision. Everywhere that f of m is 0, g of n, or wow, let me phrase it the other way. Everywhere that g of n minus m is non-zero, f of m is 0. Anywhere that f of m is non-zero, g of n minus m is equal to 0. So that means when we do the next step, where we multiply f of m at the reversed and shifted g of m at every time instant, we're always going to have a factor of 0. So that means we're going to have zeros for every instance of time. And then when we sum up across every single instance of time, from m equals negative infinity to positive infinity, we're going to end up with 0 result. So that means there's absolutely no convolution signal less than or equal to -1. We still have not figured out what happens at time n equals 0 all the way up to n equals infinity. At the next instant, here's what happens at n equals 0. So what we do is, we keep f of m in place, and then g of n minus m gets, after its reflection going from g of n to g of m, we shift it back so that it's reflected about n equals 0. Notice we do have zeros everywhere when we multiply, except for at time n equals 0, where we have a 5 times 2. So when we sum up from m equals minus infinity to infinity, we get 0, 0, 0, 0, 0, 0, 10 plus 0, 0, 0, 0, 0, 0, 0, 0. So the answer is 10. So that's the result of multiplying point by point and summing over m. So we have one more time instant figured out for our running convolution. Next, we figure out what happens at n equals 1. So we move the reflected g of m to the right by 1 more. So now we get 0, 0, 0, 0, and then 2, and then and then 5, and then 0, 0, 0, 0, 0. So what we get is 2 plus 5, or 7. So that is our running convolution. And then we can keep doing this for the next time instant n equals 2. We move it further along. We multiply across all of time, getting mostly zeros except for 3 non-zero answers, and we add them together. What's interesting is what happens, once we get to n equals 4. We notice past this point, they'll begin to overlap less and less. So here, for example, we have a, at n equals 4, g of n minus m is equal to 5, and then 1, and then 2, 2, and then 0 running backwards. So that means that, we no longer get the f of m equals 2 multiplied by something non-zero. It's now 0. So now we get, 1 times 2 plus 1 times 2 plus 1 times 3 plus 4 times 5, which gives you 27. It just so happens, the maximum of both functions coincided, so we expect to get a nice large result output for our convolution at that specific time instant. And then again, we overlap less and less until finally we get to n equals 7, where we're going to have, zeros, factors for everywhere except for at n equals 4. So we get 0, 0, 0, 0, 0, 0, 0 plus 2 times 4 plus 0, 0, 0, 0, 0, or just 8. And we know once we move past n equals 7, what's going to happen is we're going to have everywhere f of m is non-zero, g of n is going to be, g of n minus m is going to be 0. And everywhere g of n minus m is non-zero, f of m is going to be 0. So we're going to get, zeros everywhere for the rest of time for our running convolution. And with that, we have calculated from, negative infinity to positive infinity, f convolved with g of n. So you get a signal that looks like that. So in practice, we ask the computers to do convolution because it's time intensive. The relevant MATLAB function is called conv, C-O-N-V, and you put in f of g, and it basically treats the vectors as discrete functions and does a convolution for you. Here is a way to do it with a table. So we'll have, all the time instants our output is non-zero. So what we do is, first of all, we take the the first value of g of n and multiply it by f of n. So we'll get, 10 times 5 times 5 times 15 times 20. And then we'll do the next time instant of g of n, which is 1, and then we shift it over by 1. And then twice of it, shift it over another one, and then twice of f of n, shift it over another one. And then we can just sum up over all of these rows, and we also get the convolution. So some people prefer to do discrete convolution as a table. This is kind of what it's doing. Because, we can write this g of n as a sum of different, unit impulses that are scaled, so that you can write it such that we get, shifted copies of f of n that are scaled. And if that confuses you right now, don't worry, we'll get into that a little bit more when we talk about the sifting property of discrete time, or of continuous time convolution. But right now, we exploited the discrete time version to just do a nice, simple tabular version of convolution. What questions do we have to this point? Do we need convolution in the real world? What are the applications? So if we go back, we're going to use it to solve circuits. That's why we're teaching it now. Anytime you apply a filter, like if you digitally filter sound or an image, say you want to blur an image, or maybe you want to remove noise from a sound sample, maybe you want to do edge detection of an image, something like that, for machine learning purposes. What you're doing is you are convolving with a very specific function that performs a filter option. So that's how you do filtering in discrete time. Machine learning, this comes up all the time because it's basically a convolution is to some extent a measure of how two functions meld when they pass each other. So it shows how well things, it's a measure of like how one function changes the shape of another. It's very hard to come up with a physical explanation of what convolution does. Like, it's not quite like, if you have, 3 bags of apples with, 5 apples each, you have 15 apples. It's a lot harder to explain what convolution does than multiplication or any other binary operation. There are some other examples. It comes up a lot in, control signals too, but like the thing we're going to figure out is it works nicely with the Laplace transform. That's why we're studying it. You're welcome, Riyadh. Is this related to the Fourier transform? Just like we said, convolution is related to the Laplace transform. The Fourier transform is a special case of the Laplace transform. So yes, it is related to the Fourier transform. There is a convolution property of the Fourier transform that gets used. We put 2 functions back to back and multiply them where they overlap. That's mostly right for Pranav, but you have to remember you're taking one of the functions and you're also reflecting it the other way around. And then you move them past each other, or you move one past the other so that you see how much they overlap. So you take 2 functions, reflect one, and then move it past the other to see how much it overlaps. Does that answer your question, Pranav? You're welcome. Hopefully people aren't just saying I see just to make me be quiet. But like, hopefully I'm actually giving you a useful explanation. Any questions about, quiz, exam, homework 2, anything else related to this course? If not, I'm going to go ahead and call the lecture right here. Don't forget to do the quiz, sometime between now and Saturday at right before midnight. Thank you all for listening. Try your best to have a good weekend despite the homework. And if you need my help, feel free to post on Piazza to get your peers to help, or try to message a TA or me. You're welcome, everyone. Goodbye. Big, you're welcome, Riyadh. Big, you're welcome. All right. Thus ends week 2 of ECE 20,002.